We're never going beyond the moon. At least, not with humans. You've probably heard this claim before, often backed by concerns about cosmic radiation and its supposed deadly effects. Some even go further, insisting we never made it to the moon in the first place, citing the Van Allen radiation belts as an insurmountable barrier. But for those who understand the science, it's clear that space radiation, while genuinely dangerous, isn't the absolute showstopper some make it out to be. The reality is more nuanced and far more interesting. Cosmic radiation is indeed a serious challenge for space exploration. It poses real risks for missions to Mars, long-term lunar habitats, and especially for ambitious ventures like establishing colonies on Jupiter's moon Callisto or embarking on interstellar journeys. And it's not just astronauts who need to worry. Spacecraft, satellites, and sensitive scientific instruments are all vulnerable to radiation damage. The problem has been discussed extensively in scientific literature, often in simplified terms suggesting the solution is just adding more shielding, which of course adds mass, which drives up costs exponentially. But anyone who's studied the issue knows it's far more complicated than that. When planning future space missions, we carefully calculate the radiation exposure astronauts or robotic systems will face, then figure out how to mitigate those risks without making the spacecraft prohibitively heavy or expensive. Even thick shielding isn't always a perfect solution, and in some cases, it can actually make things worse through secondary radiation effects. For robotic missions, we already have decades of experience sending spacecraft to various radiation environments, from Earth orbit to the Sun's atmosphere, to the outer reaches of the solar system. We can study how radiation affected these machines and learn from their successes and failures. But when it comes to humans, our knowledge is much more limited. No person has traveled beyond the moon, so our understanding of how cosmic radiation truly affects the human body in deep space remains incomplete. Perhaps the dangers aren't as severe as some fear, or perhaps they're worse in unexpected ways. Either way, we need to understand the different types of radiation, their sources, how they vary across the solar system and beyond, and what we can do to protect both machines and people. That's exactly what we'll explore in depth. Before diving into the complexities, it's worth addressing a common source of confusion. The word radiation itself is misleading. In English, radiation can refer to any form of energy emission, including harmless visible light from a flashlight. Yet we don't typically fear light, even though technically it's a form of electromagnetic radiation. The confusion deepens when we realize that cosmic radiation is an umbrella term covering vastly different phenomena, from relatively harmless particles to highly dangerous ionizing radiation capable of tearing atoms apart at the molecular level. The type of radiation, its source, and its energy level all matter tremendously. Some radiation is easy to shield against, while other types present enormous challenges. And space itself isn't uniform. Radiation conditions near Earth differ drastically from those near Mercury, Jupiter, or in the interstellar void. Distance from the Sun matters, but so do other factors like magnetic fields and solar activity cycles. The protective measures needed for a robotic probe versus a crewed mission vary significantly, and both depend heavily on the destination. Let's start with the basics. Radiation in space comes in two main forms: electromagnetic waves, which are massless photons, and particle radiation, which includes electrons, protons, and even entire atomic nuclei traveling at tremendous speeds. We further divide radiation into ionizing and non-ionizing categories. Non-ionizing radiation includes radio waves, microwaves, infrared, visible light, and ultraviolet. While UV radiation can be harmful and cause skin cancer through photochemical reactions that produce free radicals, it doesn't have enough energy to directly ionize atoms by stripping away electrons. Ionizing radiation, on the other hand, is far more dangerous. It includes high-energy photons like X-rays and gamma rays, as well as particles such as alpha particles, which are helium nuclei, and beta particles, which are electrons or positrons. Ionizing radiation carries enough energy to tear electrons from atoms and molecules, creating ions and causing direct damage to biological tissue and electronic components. The specific damage depends on the particle's mass, speed, charge, and how it interacts with matter. Heavy ions, for example, can penetrate deeply and cause extensive damage along their path. It's amusing to consider that some people worry about Wi-Fi signals or cell phone radiation, even going so far as to put their phones in Faraday cages at night. Yet they happily spend hours outdoors exposed to the sun, a massive source of electromagnetic radiation far more energetic than any router. Some of these same individuals even skip sunscreen, despite ultraviolet radiation being a proven carcinogen. The irony is rich. In a sense, cosmic radiation has frightened humans long before we understood it. Comets, for instance, were often seen as bad omens, yet one of their tails, the ion tail, forms specifically because of charged particles from the solar wind ionizing gases. Similarly, auroras are visible manifestations of charged particles interacting with Earth's magnetic field and atmosphere. Over the past century, we've learned a great deal about cosmic radiation and its sources. In our solar system, there are two primary origins. First, there's the sun. It emits across the entire electromagnetic spectrum, including X-rays and gamma rays, and it's also a source of particle radiation. This particle radiation comes in two varieties: the steady solar wind, a continuous stream of protons, electrons, and alpha particles, and the far more dangerous solar energetic particle events, also known as solar proton storms. These occur during solar flares and coronal mass ejections, where particles are accelerated to much higher energies and pose significantly greater risks. Second, there are galactic cosmic rays, high-energy particles originating from beyond our solar system. These are primarily protons, about 85%, with helium nuclei making up another 14%, and the remainder consisting of heavier nuclei like iron. Galactic cosmic rays are far more dangerous than solar particles because the events that produce them, likely supernova explosions, are vastly more energetic. These particles travel at speeds approaching the speed of light, whereas solar wind particles move at a few hundred kilometers per second, and even coronal mass ejections only reach a few thousand kilometers per second, nowhere near relativistic speeds. Some of these particles may even originate from other galaxies entirely, though the majority come from within the Milky Way. But radiation levels aren't uniform throughout space. They vary depending on location and local conditions. Near planets with strong magnetic fields, for example, the radiation environment is dramatically different than near planets without them. Earth's magnetosphere traps charged particles, creating the Van Allen radiation belts, regions of space where dangerous particles are concentrated. Below the belts, on the International Space Station's orbit, astronauts enjoy substantial protection from Earth's magnetic field. Inside the belts, radiation exposure increases. Beyond them, in interplanetary space or on the Moon's surface, there's no magnetic shielding, so both solar and galactic particles can have much greater effects. Mars presents a similar challenge. Its thin atmosphere offers minimal protection, and it lacks a global magnetic field, leaving the surface exposed. Interestingly, though, being on the Martian surface might actually be safer than traveling through interplanetary space, because the planet itself blocks roughly half the sky, shielding you from galactic cosmic rays coming from below. In space, you're exposed from all directions. Near Jupiter, the situation is even more extreme. Jupiter's powerful magnetosphere traps enormous quantities of charged particles, creating radiation belts far more intense than Earth's. Moons like Io contribute additional material through volcanic eruptions, further intensifying the radiation environment. Solar activity cycles also play a crucial role. Intuitively, you might think the sun's active periods, when flares and coronal mass ejections are frequent, would be the most dangerous times. But it's not that simple. During solar minimum, there are far fewer solar flares, which is good. However, the sun's magnetic field weakens during solar minimum, and this reduces the sun's shielding effect against galactic cosmic rays. Just as Earth's magnetic field protects our planet, the sun's magnetic field, carried by the solar wind, shields the entire solar system from galactic radiation. When that field weakens, more galactic particles penetrate deeper into the solar system. This has profound implications for interstellar travel. Once a spacecraft leaves the heliosphere, the protective bubble created by the sun, it faces the full intensity of galactic cosmic rays without any shielding. Solar radiation becomes irrelevant at that point, but galactic rays are far more energetic anyway. And if we're talking about relativistic interstellar probes traveling at a significant fraction of light speed, the problem becomes even worse. The spacecraft's velocity combines with the energy of incoming particles, resulting in devastating collisions. All of this makes clear that cosmic radiation is a multifaceted problem. We must consider where we're going, what type of mission it is, whether it's crewed or robotic, what radiation sources dominate in that region, and when we're launching relative to the solar cycle. There's no one-size-fits-all solution, and simply wrapping everything in lead isn't practical or even advisable. Lead and other dense materials can actually produce secondary radiation when struck by high-energy particles, sometimes making the problem worse. So, how exactly does radiation damage spacecraft and equipment? At its core, the process involves a high-energy particle penetrating a material and transferring its energy, which causes harm. The specifics depend on the type of radiation, the properties of the material being struck, and the surrounding environment. The most common mechanism is ionization, where incoming particles strip electrons from atoms in the spacecraft structure or electronics, or add extra electrons, disrupting the material's properties. Ionization can occur through several pathways. Charged particles interact directly with electrons and nuclei in the material. Neutral particles like neutrons cause ionization through direct collisions. High-energy gamma-ray photons can knock electrons out of atoms or interact with atomic fields to create electron-positron pairs, which then annihilate and produce more gamma rays, perpetuating the cycle. There's also Bremsstrahlung radiation, where charged particles passing through matter interact with electric fields, causing the particles to emit additional photons, creating something like a shock wave of secondary radiation. When cosmic rays strike atomic nuclei, they can alter or fragment those nuclei, producing additional secondary radiation that's also dangerous. This cascade effect means that a single incoming particle can trigger a chain reaction of damage. These interactions cause several problems for spacecraft. One issue is charging. Spacecraft surfaces, especially in environments like low Earth orbit, can accumulate electrical charge. This creates potential differences between the surface and the surrounding plasma, or between different parts of the spacecraft. Charge can also build up internally within instruments and components if particles penetrate deep enough, which is often more dangerous. These charge differentials can lead to electrical discharges that cause both structural damage and malfunctions in microprocessors, sensors, and other electronics. The severity of damage varies. Minor errors might be correctable with a simple reboot, while severe damage can be permanent. There's also the phenomenon known as single event effects, where just one high-energy particle, perhaps a galactic cosmic ray proton, strikes a microchip and causes a critical error. Beyond single events, there's the concept of total ionizing dose. Over time, cumulative radiation exposure can reach levels that completely destroy a spacecraft's electronics, rendering it inoperable beyond any possibility of recovery. The first satellite ever destroyed by radiation overdose wasn't a victim of natural cosmic radiation. We did it ourselves. The satellite was Telstar 1, launched in 1962. That same year, the United States conducted high-altitude nuclear tests under a program called Starfish Prime. A 1.4 megaton warhead was detonated at an altitude of 400 kilometers, roughly where the International Space Station orbits today. The explosion produced vast quantities of beta particles that became trapped in Earth's magnetic field, creating an artificial radiation belt that persisted for several years. Telstar received a radiation dose 100 times higher than it was designed to withstand and failed. That nuclear test ultimately destroyed 7 satellites, mostly through damage to their solar panels. Cosmic particles also cause mechanical and structural damage at the atomic and molecular level, creating microscopic defects that accumulate over time. The type and extent of damage depend heavily on location. Even near Earth, conditions vary significantly. There's a region called the South Atlantic Anomaly, where Earth's magnetic field dips closer to the surface, allowing trapped radiation belt particles to reach lower altitudes. Spacecraft passing through this region experience higher radiation doses, and sensitive instruments often have to be powered down temporarily to avoid damage. For satellites in Earth orbit, we have a fairly good understanding of radiation effects after launching thousands of them over decades. But for missions venturing into interplanetary space, our data is much sparser. When a distant spacecraft experiences problems, we can't always determine the cause with certainty, partly because we don't fully understand the environment it's operating in. Still, there have been clear cases where cosmic radiation was almost certainly to blame. Consider the Galileo spacecraft, which studied Jupiter and its moons from 1995 until 2003. Galileo operated in one of the most intense radiation environments ever encountered by a spacecraft, far exceeding its design limits. The mission experienced numerous radiation-related failures. For instance, the star scanner, used for navigation, sometimes mistook signals from cosmic rays for actual stars. This caused the spacecraft to think it was pointed in the wrong direction and triggered unnecessary attitude corrections. When data from the star scanner conflicted with gyroscope readings, onboard fault detection systems would switch Galileo into a different operational mode. On one occasion, this happened twice within 8 hours, and had it occurred 2 more times, the spacecraft would have entered safe mode, suspending science operations. There were other issues as well. The high-gain antenna, which was supposed to deploy after launch, never fully opened, forcing the mission to rely on a much slower low-gain antenna for communication. While this wasn't directly caused by radiation, radiation did damage other systems. Memory chips experienced bit flips. Cameras and spectrometers suffered from noise in their data. Particle detectors malfunctioned. The list of affected instruments was extensive, and mission engineers had varying degrees of confidence about whether radiation was the culprit in each case. Despite these challenges, Galileo operated far longer than its planned mission duration and returned invaluable scientific data. But the experience highlighted just how little we know about radiation in distant parts of the solar system. The farther from Earth we go, the less we understand. Yet the Voyager spacecraft, launched in 1977, continue to operate nearly 5 decades later, even beyond the heliosphere, sending back unique data about interstellar space. Admittedly, Voyager probes are much simpler than modern spacecraft, which may partly explain their longevity. This dual reality defines our situation. On one hand, we've been launching spacecraft for decades, and they generally work. On the other hand, mission parameters are set with radiation risks in mind. If we could eliminate or better mitigate those risks, missions could last longer and accomplish more. The farther and more complex the mission, the greater the risk. Simply hoping radiation won't cause serious problems or destroy a spacecraft entirely isn't a viable strategy. We need better shielding and protection methods. And when it comes to human spaceflight, the stakes are infinitely higher. On Earth's surface, we're fortunate. Our dense atmosphere and strong magnetic field provide excellent radiation protection. Most cosmic rays never reach the ground. Those that do have already lost much of their energy. Even at high altitudes, radiation exposure increases but remains manageable. Commercial airline passengers and crew receive slightly elevated doses, roughly equivalent to a dental X-ray per flight, but it's not a major concern for occasional travelers. Frequent flyers and air crew do accumulate higher lifetime doses, which is monitored, but it's still far below dangerous levels. Astronauts on the International Space Station face a different situation. They're above most of the atmosphere but still within Earth's magnetosphere, which provides substantial shielding. Radiation exposure on the ISS is carefully tracked, and it's higher than on Earth's surface, but manageable with current safety protocols. During solar storms, astronauts can move to better shielded sections of the station to reduce exposure. So we know that humans can safely live and work in low Earth orbit for extended periods, provided certain precautions are taken. But doubts arise when we consider missions beyond low Earth orbit. Some of the data is genuinely concerning. A study published in the journal Nature noted that beyond low Earth orbit, every cell nucleus in the human body would be struck by a proton or secondary particle roughly once every few days, and by a heavier ion like silicon or iron once every few months. Personally, the idea of dangerous particles constantly tearing through every cell in my body is deeply unsettling. And even though heavy ions are rare, they account for a disproportionate amount of the radiation dose because of their high energy and mass. These heavy ions can cause clustered damage to DNA, breaking both strands simultaneously in ways that are difficult for cells to repair. This leads to mutations, cell death, and significantly increased cancer risk. Radiation also affects the cardiovascular system, increasing the likelihood of heart disease. It can damage the central nervous system, potentially impairing cognitive function, memory, and decision-making. For a Mars mission, where astronauts need to perform complex tasks and make critical decisions, cognitive impairment could be catastrophic. There's also the issue of acute radiation sickness. A major solar particle event during a mission could deliver a dose high enough to cause immediate symptoms: nausea, vomiting, fatigue, and in extreme cases, death. Astronauts would need advance warning and access to a heavily shielded safe haven, essentially a storm shelter inside the spacecraft. We study these risks using various methods. Animal studies provide some data, though they don't perfectly replicate human physiology. We also use computer models to simulate radiation exposure during hypothetical missions, taking into account spacecraft shielding, mission duration, and solar activity. These models help estimate cancer risk, cardiovascular effects, and other health outcomes. Data from astronauts who've flown in low Earth orbit provides another piece of the puzzle, though it's not directly applicable to deep space missions where radiation levels are much higher. Some researchers have proposed using particle accelerators to simulate cosmic rays and study their biological effects in controlled environments. Despite all this research, significant uncertainties remain. For a mission to Mars, current estimates suggest astronauts would receive at least 60% of their entire career radiation dose limit just during the round trip, not even counting time spent on the Martian surface. That's a sobering statistic, and it raises serious questions about the feasibility of crewed Mars missions under current safety standards. So what can we do about it? Shielding is the obvious answer, but it's complicated. Passive shielding involves placing material between the radiation source and whatever you're trying to protect. The challenge is finding the right material. Dense metals like lead are effective against some types of radiation, particularly X-rays and gamma rays, but they're heavy, and weight is a critical constraint in spaceflight. Moreover, when high-energy particles strike dense materials, they can produce secondary radiation through nuclear interactions, sometimes making the problem worse. Hydrogen-rich materials, like polyethylene or water, are much better for blocking charged particles. Hydrogen nuclei are single protons, and when a high-energy particle collides with a hydrogen atom, the collision is more likely to scatter the particle and absorb its energy without producing as much secondary radiation. Water is particularly appealing because it serves multiple purposes: drinking water, radiation shielding, and potentially propellant if split into hydrogen and oxygen. Some spacecraft designs incorporate water tanks into the hull structure, specifically for radiation protection. There's also active shielding, which uses electromagnetic fields to deflect charged particles, much like Earth's magnetosphere. This concept is elegant, but technically challenging. Generating a magnetic field strong enough to deflect high-energy cosmic rays requires superconducting magnets and substantial electrical power. The field would need to extend far beyond the spacecraft to be effective, which means large, lightweight coil structures. And magnetic fields only deflect charged particles, so they don't help against neutral particles like neutrons or against electromagnetic radiation like gamma rays. Electrostatic shielding is another active concept, using charged surfaces to repel incoming particles. Again, this requires power and only works against charged particles. Researchers are exploring hybrid approaches that combine active and passive shielding, using magnetic fields to reduce the number of particles reaching the spacecraft and lightweight materials to absorb what gets through. This might be the most promising strategy, balancing protection with weight and power constraints. Another approach involves mission timing and trajectory planning. Launching during solar maximum, when the sun's magnetic field is strongest, reduces exposure to galactic cosmic rays, though it increases the risk of solar particle events. Trajectories can be optimized to minimize time spent in high radiation zones, such as the Van Allen belts or Jupiter's magnetosphere. Spacecraft can also use planetary bodies for shielding, positioning themselves so the planet blocks radiation from one direction. For Mars missions specifically, one idea is to land in lava tubes or other natural caves, which would provide excellent radiation shielding without requiring massive construction efforts. Habitats could be buried under regolith, using Martian soil as a radiation barrier. On the Moon, similar strategies could work, and some designs propose 3D printing habitats using lunar regolith mixed with binders. Biological countermeasures are also being researched. Certain drugs, called radioprotectors, can reduce radiation damage if taken before exposure. Antioxidants help neutralize free radicals produced by radiation. Gene therapy might one day enhance the body's natural DNA repair mechanisms. These approaches won't eliminate radiation risk, but they could reduce it to more acceptable levels when combined with physical shielding. There's also the question of acceptable risk. Astronauts are not ordinary civilians. They're highly trained professionals who accept significant risks as part of their job. Fighter pilots, deep-sea divers, and mountaineers all face life-threatening dangers, and society accepts this because they do so willingly and in pursuit of important goals. Space exploration is no different. The question isn't whether we can reduce radiation risk to zero, which is impossible, but whether we can reduce it to a level that informed, consenting individuals are willing to accept. Current NASA guidelines set career radiation dose limits based on keeping the lifetime risk of cancer mortality below 3%. That's a statistical risk, not a certainty, and it's comparable to risks accepted in other professions. For a Mars mission, astronauts would likely exceed this limit, which means either the limit needs to be raised, or waivers need to be granted, or we need better shielding technology. All three options are on the table. Looking further ahead, interstellar missions present even greater challenges. Outside the heliosphere, galactic cosmic ray intensity increases significantly. A spacecraft traveling at 10% the speed of light, which is considered a realistic target for an interstellar probe, would experience devastating particle collisions. At that velocity, even collisions with individual hydrogen atoms in the interstellar medium release tremendous energy. Cosmic ray particles, already traveling near light speed, would strike the spacecraft with combined kinetic energies capable of vaporizing material. Shielding an interstellar spacecraft is a problem that borders on science fiction. Some concepts involve placing sacrificial material at the front of the spacecraft to absorb impacts. Others propose using powerful magnetic fields extending thousands of kilometers ahead of the craft. There are even ideas involving plasma shields or clouds of charged particles generated by the spacecraft itself. None of these have been demonstrated, and all require technology far beyond our current capabilities. But here's the essential point. Radiation is a serious challenge, but it's not an unsolvable one. We've already sent humans to the moon and back, and while they passed through the Van Allen belts, they did so quickly and received only minimal doses. The Apollo missions demonstrated that with proper planning and shielding, the belts are not an impenetrable barrier. For Mars missions, the radiation risk is higher, but numerous studies suggest it's manageable with better shielding, mission timing, and possibly biological countermeasures. Robotic missions have operated successfully in harsh radiation environments for decades. Galileo survived years at Jupiter, despite exceeding its design limits. The Voyagers are still functioning in interstellar space. New materials are being developed that are lighter and more effective at blocking radiation. Perovskite materials, for instance, have shown surprising resilience in radiation tests, even exhibiting self-healing properties when exposed to high-energy particles. Advances in superconducting magnets could make active shielding more practical. Improved electronics with radiation-hardened components can better withstand the space environment. Recent solar activity has provided real-world data. In January 2026, a severe solar radiation storm, the most intense in over 2 decades, struck Earth. Radiation levels spiked, affecting polar flight routes and satellite operations. The International Space Station experienced elevated radiation, and astronauts took precautions. But systems held, and no catastrophic failures occurred. Events like this help us refine our models and improve our preparedness. Ultimately, the future of human space exploration depends on our ability to manage radiation risk, among many other challenges. It's not an absolute barrier, but it does require serious engineering, careful planning, and acceptance of some level of risk. The same could be said for virtually every aspect of spaceflight. Launch vehicles can explode, life support systems can fail, Micrometeoroids can puncture hulls. Yet we continue to fly because the potential rewards outweigh the risks. Radiation is one piece of a complex puzzle. Solving it won't be easy, but it's solvable. With continued research, technological development, and a realistic assessment of acceptable risk, humanity will continue to push farther into space. We'll return to the moon, establish a permanent presence there, send crews to Mars, and eventually venture even farther. Cosmic radiation is dangerous, yes, but it's a challenge we can meet. The question isn't whether we can go beyond the moon. It's how soon we'll get there, and how far beyond we'll ultimately reach.